Okay, welcome to the week 3 material. We're going to leave set behind for a bit. We're going to talk about propositional logic. Now, propositional logic starts with a bunch of base propositions. Those we will just represent by letters, and we will assume we have some way of determining whether they are true or false. We don't care about that. What we care about is how we can combine the logical truth or falsehood of these statements to get more complex statements. And we'll do that using logical connectives like and, or exclusive or negation. And we will work out what the values of these will be in the same way that a circuit with an OR gate or an AND gate or whatever it is will output something, so a plus or a minus, based on the plus or minus of the two input signals. So we're going to try to behave in this part of the course like the very most fundamental piece of electronics that make computers work. Okay, let's have a look at propositional logic. So this is a very grand word for what is the most basic form of combination of logical statements, but the reason it's called this is because we start with a bunch of propositions. So start with a set, and we can make it as large as we want, basically, but a set P, Q, R, etc. Of what we're going to call propositions. And we can use these to represent kind of statements in mathematics or statements in just plain English. But the main point about them is that they are either true or false. There's no other possibility. So each is either true or false, and we are interested in how to combine them. And the best way to do this is with an example, as usual. And so we will start with conjunction. So if P and Q are propositions, I'll just say props, then P and Q is also a prop, so a compound prop, compound proposition, just because it's made up of more than one thing. We write it with a wedge, and the reason it's with a wedge is because it should look like intersection. You're intersecting the things that are true with the things that are true and looking at when they're both true. And it is true if and only if both P and Q are true. So it's at this point that we want to introduce truth tables. The idea is that because P and Q only could be true or false, there are only two possibilities for P and two possibilities for Q. So there's only four possibilities that we have to look at to decide the truth of anything that just depends on only two propositions. So we should be able to write them all out in a table. So, and that is what we will do here. So this is our first truth table. You want to put P, and then you want to put Q, and then you want to say what that means about P and Q. So, as I said, there are two possibilities for P and Q each. So let's just sort of run through them in a kind of binary way. FF, those are the four possibilities. And I'm just going to tell you whether these are true or not. So if you get true and true, then P and Q is true. And if that's the only time it's true, and so the others are false. Okay, so let's have an example. Let P be a statement, i.e. olives. I'm talking about myself here. I have no idea whether you eat olives. And I'll let Q be the statement, olives are delicious. Right. And I've told you that this first statement, P, is true. It is true that I eat olives. I'm also telling you that it's true that olives are delicious. So I don't care what your opinion is, but Q, for the purposes of this, is true. So if I want to know whether P and Q is true, if it's the statement I eat olives, that's true, and olives are delicious, which they are, then P and Q is true. P is true, Q is true, and so P and Q is true. Okay, and obviously if you had a different statement like, you know, I eat olives, that's still true, and Q is the statement olives are disgusting, then that would be false, and so P and Q would be false. Okay, so conjunction corresponds to taking the intersection of sets and has a corresponding notation that looks like intersection. So there must be something that looks like union, and that is called disjunction, and it corresponds to the word or. So so P or Q is the disjunction of P and Q, and we write it with a instead of a wedge, we write it with a what's called a sort of V, and it has that symbol. Obviously, it looks a bit like what you do when you're writing union. So it's a sort of cup thing, but with an angle. The truth table. So it's this is going to be true when at least one of them is true. So in the same way that you we take it that or in this situation is an inclusive case, it will be for this as well. Let's just write down the truth table and all will become clear. So if P is true and Q is true, then that's fine. It's true that P or Q is true. If at least one of them is true, it's still true. If at least one of them is true, it's still true. The only time it is false is when you have both of them being false. So that's the only time that the or is false. And I'll just say that, so we use or inclusively. So sometimes you give people or as a choice. So if you have a kid that's misbehaving and you say either you eat your greens or you go to bed, right? You don't leave the option open that they might both eat their greens and go to bed. The question is then to make a choice. But so in English it can be used exclusively. Logically, we will always use it inclusively. Right. So that leads us very swiftly on to exclusive disjunction. Exclusive disjunction. I won't write that out again, but it's the same word as above. So this is P, X or Q, and it's the very thing I just told you we're not going to use. So we write it as P direct sum with a plus with a circle around it, Q, and the truth table is as follows. And it's just what you get when you say P is true or Q is true, but not both. So let's have a look at that. So I've just said if they're both true, then it's false. If one of them is true, it's true. Exactly one of them is true, it's true. But if both of them are true, it is false. So there is an example of that. This is a bit like flicking a switch if you think about it. If the switch is turned on and then you flick the switch to on, if you have two of them in parallel, if you flick two switches then it goes off, but if you've only flicked one of the switches then the light is on. If you have a light system that uses two switches. Okay, very good. Now, an even simpler idea is negation. And that's going to be written like this. So that's a little sim or tilde symbol. And this means not P. This is not P. So all it does is it just reverses the signal from P. So if that's P, then not P is just going to be the opposite. Okay. Now we're going to come to the most sort of conceptually difficult one, which is but the most important for the purposes of reasoning, which is the conditional. So conditional statements are where you have something, if something is true, then something else is true. So if P, then Q. So if you have something like that, you write it in the following way. So it's saying if I know the truth of P to be good, if P is true, I can take from that the truth of Q. So how does that work as a truth table? So all I'm saying about in that statement is I don't care if P is false, then I have nothing to say on the matter. But if I know that P is true, then I must know that Q is true. or the statement I'm making is false. So let's write that down. So if P is true, then Q has to be true according to this statement. So when it works, then my statement is true. The only time it doesn't work is when I know that P is true, then Q is false. So in that case, I mean that this conditional should be false. But otherwise, I don't care. So if P is false, I'm making no promises about anything at all. And so I take from that the conclusion that that P implies Q is true. Okay, I just want to draw your attention to a feature of this table. If P is false, then it doesn't matter what Q is. This implication is always true. This can create some rather weird situations. So if I say something like, I am a pumpkin, which is false, by the way, I'm a pumpkin and therefore you are one. This is true. This implication is true. I am a pumpkin and I'm the only one and therefore you're not. Well, you aren't a pumpkin, but this implication is still true. It can be strange to think, why on earth would one want to use truth in this way? But it helps you to break down where an argument goes wrong. So the implication process could be fine, but if you've started with something wrong, then you know to go back and say that that's wrong. It's basically the same as a proof by contradiction. So false implies everything. That's what you need to remember. Here's a sort of mathematical way to see it. So you would agree, I'm sure, that 0 times 1 is the same as 0 times 2. Now, we may always, I'll just say it like this, we may always cancel from both sides. So we may always cancel from both sides is a reasonable sounding statement. So getting rid of the zeros, we get 1 equals 2. Okay, this is a perfectly reasonable implication. If it's true that we may always cancel from both sides, then we do get 1 equals 2. The problem is we can't always cancel from both sides in the way that is being done here, because it's dividing both sides by 0. So if we've got an absurd conclusion, it must be, therefore, because of this table, that the thing I started with was false. And the thing that's false here is we may always cancel from both sides. So this is why this kind of this idea is useful, because it allows you to make arguments and see if something is absurd, and then know that somewhere in that argument you made a hypothesis. In other words, you assumed the truth of a proposition which is false. Okay, I'll pick this up later.